related to my research for a couple of years now. Okay, so I will end. One more thing is that because my background is computer science and electrical engineering, so maybe the mathematics is not quite rigorous to you guys in the maths department. Okay, so I apologize in advance. Okay, uh, okay, so image processing. So it's a very classical field. Okay, and the first known textbooks on this is by Rosenfeld, uh, picture processing by computer in 1969. Okay, so image processing can be seen as applying fundamental signal processing methods to 2D signal, which is um, digital images. As you can see, for example, like in this book, two-dimensional signal image processing. So images are just 2D signals. Okay, so and then it has numerous applications, and some of them are segmentation, restoration, compression, and many more. Okay, so image restoration. Okay, so I'll be focusing mainly on image restoration in this talk. Okay, so it's a very fundamental theme in image processing. I think it has been studied for several decades now, up until now. The latest cutting edge is using deep learning models to do image restorations. Okay, so the objective is to estimate a clean image from its corrupted version, and the corruption can be these are the corruptions that are normally in certain image restoration. We have blur, we have noise, and sometimes also we will have a blur plus some noise. Okay, and this noise is there are many types of noise, and I will try to discuss them a little bit in this talk also. Okay, and this restoration can be done by traditional filtering methods. Okay, you have the mean filtering, median filtering, so those all those traditional methods, and also can be done by variational methods, which heavily involves mathematical optimization. So I will be focusing on these variational methods in this talk. Okay. Okay, so now we have the image degradation model. Actually, it doesn't not it's not just for images, it's also for signals. Okay, so this is just to show you, okay, the assumption of the image degradation that we are using throughout this talk. Okay, so the we have this f is equals to ku plus n, and f is the corrupted image. Okay, your observation. Okay, for example, you take a camera and then you have a corrupted like blurry or noisy image. Okay, so that's your observation. And then you have k, it's a linear operator. Okay, we assume it's a linear operator. So in this talk we will focus on the k being a blur. Okay, you can have other other linear operators. For example, if you for those who are in the pure signal processing, we have the compressed sensing, right? Compressed sensing. So this k can be random measurement matrix. Okay, and then u is the clean image that we want to estimate. Okay, so this is the clean image that we want to estimate, and we have the noise. Okay, the additive noise. Okay, so it's something like this. Okay, if you want to picturize this equation. Okay, so so this operator over here is a if it's a blur, then it's a convolution operator. Okay, it's a convolution operator. Okay, so so estimating the image u, it's a very difficult problem. Okay, even if you don't have the noise, for example, in the previous slide here, even if you don't have this noise, it's still very difficult. Because as we know in our linear algebra course, you can just take the inverse, right? So, but for this image degradation or image restoration, even if you just take the inverse of this, you won't get a satisfactory result. It's very difficult because of this. K usually has a very big condition number. It's and it's very sensitive to yeah, it's very sensitive and it's ill post. Okay, so what people have been doing for several decades to estimate the image U just now is by regularization methods. Okay, so this will involve minimizing this type of cost function. Okay, so you have this you have two functions actually. Okay, so the function f in the literature, in the image processing literature, we call this the data fidelity. Okay, which depends on the noise statistics of the corrupted image. Okay? And the function g, we call it the regularizer or the penalty function. So this one depends on the prior knowledge of the image. Okay, so we will discuss this. What is this prior knowledge and the types of noise statistics after this. Okay, so um, so we will in variational methods we will minimize this using various algorithms. Okay. Okay, so the motivation of, I just want to give some motivation of how did they come up with this minimizing this two functions, the composition of these two functions over here. So if you look it into optimization lens, okay, it can be posed as this noise constraint optimization problem. Okay, you minimize this some function f, okay, subject to the this constraint over here. Okay, so we assume that the noise, okay, is bounded. Okay, so by this this amount of over here. Okay, so if you construct the Lagrangian function of this, okay, so you will have this minimize and this function, okay, plus this term over here. Okay, so when this mu, okay, which is larger than 0, controls the amount of noise filtering. Okay, and also controls the constraint, so that this constraint is satisfied. Okay, so this is if you look into this as a motivation from the optimization lens. Okay, so another motivation for the regularization method, equation 3 just now, which is this one, I'm referring to this. Okay, this one is statistical motivation. Okay, so I'm not expert in statistics, but I just know a little bit on related to this field. Okay, so just bear with me if maybe there's some mistakes over here. Okay, but I try to uh, read the literature and be precise. Okay, so it's comes from the maximum a posteriori estimation, map estimation of U in the image degradation model 1. Okay, the image degradation model. So you have this this, okay, map estimation. Okay, so you have this so this probability over here is the posterior distribution of the clean image to be estimated. Okay, because we want to estimate the image U, right? Okay, from the degradation model. And we have this one over here is the posterior distribution representing the probability of obtaining the degraded image F, okay, given the clean image. Okay, and you have this over here, this probability over here is the evidence term, and this probability is what we call the prior probability. Okay, so if you look at this map estimation over here, so this evidence term is just acts as a normalizing constant, and even if you minimize this after this, it does not depend on U. So we can just remove this. Okay, And if we take the logarithm of this equation over here, of this equation 4 over here, and you maximize or minimize, okay, over u, so you have like this equation 6, okay. So that one, if you maximize, if you minimize, then you change the sign, right? So then you will have this minimize, okay, because we want to find the image, okay, over here, and then you have this probability, and this one did the prior probability over here, okay. So if we assume that the this probability over here is a zero mean, independent, and identically distributed Gaussian noise, okay, which is this, okay, this probability over here, okay, and if we have this prior probability, okay, this prior probability is assume that it has a Gibbs distribution, okay, because it is found that if you look into the pixel values of an image, okay, they do not really change very abruptly between the pixels, okay. So that is modeled by this Gibbs distribution, and then you have this. So that's why you have this probability over here is this one, the equation 8 over here, okay. And R is some energy function, okay. So if you take into this Gaussian over here, this Gaussian, and also this Gibbs, sorry, yeah, this one, this Gibbs distribution, and you substitute that one in equation over here, this one, you substitute here, okay, and then you do the simplifications and so on, then you will get this regularized objective function, okay. So that's why I wanted to motivate how did they come up with the regularize this formula over here, okay. So you'll get the data fidelity and the regularizer. So and so this regularizer, this can take many forms, okay, and we will discuss that after this, okay. So in this case, okay, this equation 11 over here, so you have this we assume that the standard Gaussian distribution, which is we have over here, this one is equals to 1 from the previous equation, this one. So that's why you have 1 over 2 over here, okay, just the standard Gaussian distribution. Okay, so this one, okay, so that motivation was just an example for the Gaussian noise, because we used the probability was the Gaussian, right? Gaussian distribution. So that's why we got this from that we got this L2 norm. Okay, so if we assume different types of noise, okay, this term will be different. Okay, the data fidelity will be different. Okay, so this one, if you look into this equation 11 over here, it will be, if you minimize this, okay, for the image processing, image restoration purposes, it's going to be more suitable for Gaussian images that are corrupted with Gaussian noise. Okay, so this regularizer can be an L1 norm, L2 norm, and even the LP norm, which is P between 0 and 1. However, if you have the LP norm and P is between 0 and 1, it will be a non-convex optimization problem. Okay, but in this talk, I will just focus on when this R, okay, this function R is going to be L1 norm and L2 norms. Okay. Okay, so this is what I alluded for before in the previous slide. If you have different probability distributions, for example, you have the Poisson noise distribution, then you'll use this one, impulse noise, like this, okay, and also the regularizer. So in this talk, the regularizer R, okay, the R function, will focus more on the what we call the total variation regularizer. Okay, so it's defined as this one. Okay, you have the this is going to be this D over here is the discrete first order difference operator, and you have it. It's going to be this one is the L1 norm. Okay. Okay, so I want to talk a little bit about this total variation regularizer. Okay, so this so it embodies, as we mentioned just now, the regularizer is going to it's the prior knowledge of you, right? If you recall back to several slides that I presented just now. So what is this prior knowledge of the image? Okay, so this total variation TV regularizer. Okay, so this embodies the prior knowledge that the gradients of an image is sparse. Okay, so gradients of image is sparse. I will show a figure after this and see what it means by the gradient of an image is sparse. Okay. So this D over here, this D over here is this is how you define this. Okay, it's the discrete first order difference. Okay, so this is what I said just now, the sparse gradients. So if you apply this operator D on an image, okay, you will find out that you will get this like this. So if you can see this black pixels and only some of the like you can see the contours, right? The contours is, so they are sparse. You have the black pixels and also the almost the white pixels. So and they're very sparse. Okay, so this embodies the sparse gradients, okay, of an image. Okay, so and that is what we use as a prior knowledge, and that is why we use the first order, the TV regularizer. Okay. Okay, so now as a first motivation for regularization methods, okay, for image restoration, we will look into this Tikhonov functional that we minimize, okay, for image denoising. Okay. So you can see this old fellow over here is Andrei Tikhonov. Okay, he was the one who was the pioneer in this Tikhonov regularization method. Okay, so this is the model, Tikhonov functional model, that if you minimize this, then we can get the filtered image U. Okay, so this over here, this parameter over here, lambda, so is what we call the regression parameter, which will control the amount of noise filtering. Okay, and D is the first order difference operator, like we've discussed in the previous slide. Okay, so so if you look into this Tikhonov regularization functional, okay, so it's actually a quadratic, so it's smooth and convex. So that means that you can minimize this using first order optimization algorithms such as gradient descent, heavy ball method, and Nesterov's accelerated gradient descent. What we have to do is we can just compute the gradient of this. So if you compute the gradient of this, then you'll get this, and then you can just substitute that in the algorithm for either GD, HB, and AGD. For example, if you have gradient descent, so this is the step for the gradient descent. You just have to substitute the gradient with the gradient of the Tikhonov functional, and heavy ball method. Also, you just substitute where you have the gradient of the Tikhonov function over here, right? And also the accelerated gradient descent. Also over here, I didn't substitute the value of the gradient, but you just have to substitute the gradient over here. Okay. So if you minimize the Tikhonov functional just now by these three methods, okay. So these are just some example. Okay, example, and I use we have this image, MRI image of this feet. Okay, so we have this noisy image. Again, this one is minimizing the Tikhonov functional by the gradient descent. Okay, so you can see some improvements because the noisy is 20.67 decibels, and then you have some improvements. Okay, this is by minimizing using the heavy ball method. Okay, you have also some almost similar results because these are essentially just related to acceleration, but they are essentially their base is the gradient descent, right? Gradient descent. They are just these are just variants of the accelerated versions of the gradient descent. Okay, so that's why the descent of values, the improvements are almost similar. Okay, so and these are some of the setup that we use for this very this simple example over here. All right. Okay, if you look at the observation, what we can see is that if we minimizing this Tikhonov function, okay, it's you can see it's blurred and smoothen out. Okay, sharp. Okay, it's not sharp. So the problem is that we want to have a model that preserves this sharpness. Okay, because sharpness will because you compare to the ground truth over here, it's very sharp. Okay, so we want to have some model that can preserve this sharpness. Okay, so which we will have the total variation model. Okay, so total variation model is this one, equation 15 over here. Okay, the only difference is we substitute the L2 norm just now in the from the Tikhonov regulation with the L1 norm. Okay, as you can see, it's still going to have this L1 penalization in the discrete gradient of the image, right? Okay, so that is the only difference. Okay, however, even with this simple difference, the problem is this L1 norm is non-smooth and non-differentiable. Okay, so this total variation is very very popular in image restoration. Okay, it was firstly introduced by this paper over here, and this Rudin, Osher, and Fatimi. So this is Stanley Osher, one of the authors of this, who created this total variation model for image restoration. So if you look into this paper in the Google Scholar, you will see that it has almost 20,000 citations. It's very, very popular image restoration model. Okay. Okay, so because of non-differentiable and non-smoothness of the total variation regularizer just now, so we cannot use the first order methods. Okay, because you cannot compute the gradient of the L1 norm. Okay, so we have to use a specialized algorithm, and the first algorithm I want to overview is the ADMM, which is the alternating direction method of multipliers. So this ADMM, it's going to minimize this type of problem. Okay, so we have this F and G, and then it's this constraint. Okay, and you have this constraints on the function F and G. Okay, and you have all of this. These are linear operators A and B, and you have D, and then the so the first step in the applying the ADMM to optimization problem of this form is we have to construct the augmented Lagrangian function, which is like this. Okay, and over here you have the Lagrange multiplier. Okay, and this rho is the penalty parameter. Okay, for the constraint. All right. Okay, so and then after that we the objective is to find the saddle point of this augmented Lagrangian function, and then we can alternately minimize the variables separately, which is the U subproblem, the V subproblem, and the Lagrange multiplier, updating the Lagrange multipliers over here. Okay, so this is the general form of the ADMM, okay, for that type of problems. Okay, so we will see how we can apply this total variation restoration, okay, for using ADMM. So this is the TV problem. So if you do the substitutions, okay, A is equals to D and so on over here, you will get that it's going to be in this form. So this is going to be amenable to the ADMM, okay, and then you just construct the augmented Lagrangian, okay, function of this problem. We will have this, okay, and then yeah, we alternately minimize the between U, V, and the Lagrange multiply update. So this is the overall ADMM to solve the total variation denoising problem. Okay, so this one is, I have some remarks over here, is that this U sub problem over here is going to have, we have to solve a linear system. Okay, and then over here is this has a closed form solution, which is in forms of the soft thresholding. We'll go into that. Or if I think some of you know the proximal operator. This one is like the proximal operator. Okay, and then we have the Lagrange multiplier updates. Okay, so so the first step, which is the linear system, usually people will solve it using conjugate gradient method, several iterations of conjugate gradient method. If we assume periodic boundary conditions for the image, sometimes people will use the solving the linear system in the Fourier domain by using 2D Fourier transforms. Okay? But usually in the real world application, we don't have we don't know the blur actually in real world application. So people will stick to using several iterations of conjugate gradient method. And step 2, which is you have this soft thresholding, or the solution to a proximal operator, which you have this closed form solution. Okay. Okay, so this is an example. Same image, okay, using noisy. You have this noisy image, okay, and then you can see this. This one is the noise level is just is 22.86. Okay, so we have a PSNR value of 20. So if you denoise this using ADMM with this setup over here, you have quite large improvement, 29.38 decibels. Okay, and this one over here, the bottom image is I increase a little bit the noise, which is you have the noise level is 40 over here. Okay, so you can see the PSNR value is quite low, 16.10. And if you denoise this using ADMM, you will get up to around 27.38. So it's as you if you compare the image, actually I should have put one of the image of the one using the first order method over here, but you can see it's more sharp compared to the if you use the Tikhonov regularization with the first order methods. It can preserve the sharpness of the image if you compare these two images to the ground truth. Okay. Okay, so in terms of the denoising capabilities is quite good, ADMM, but it has a slight disadvantage, which is we have to solve the linear system, right? So linear, because if you have a very large image, then you have not just the overall ADMM iteration, this one, you have also an inner iteration because you are using some, for example, you use the conjugate gradient method, right? So you will have also the iteration for the conjugate gradient method. Okay. So that is just one slight disadvantage of this EDMM. You have to solve the linear system. So the question is now, can we avoid this linear system? So yes, we can avoid this linear system. By the way, for the denoising examples that I showed just now over here, the linear operator that we discussed, uh, this one, yeah, this linear operator is going to be the identity, okay, the identity matrix, okay, because we don't have any blurring. There's just noise only, okay. So there's no blurring in the corrupted image, just noise. So the K is going to be the identity of matrix. Okay, so how to bypass the linear system in the ADMM? So there's one algorithm that can actually, there are many, of course there are many algorithms, but one of them that I want to just overview is Seng's alternating minimization algorithm, or I just call this AMA. So this is Paul Seng. He was the one who introduced this in this paper over here in 91. Okay, but unfortunately Paul Seng went missing in 2009 when he went to I think he went to kayaking in China, and then he disappeared. Okay. So he introduced this. Okay, so why I want to just overview this algorithm, because it's quite similar to the ADMM. Okay, it minimizes the augmented Lagrangian function like the ADMM. However, also in one step of the algorithm, it will also minimize the Lagrangian function. Okay, so this algorithm, at least in image processing, is not very popular compared to ADMM. If you look around in Google Scholar, just I think maybe just around not more than 20 papers use this for this AMA for image processing. Very few. Okay. Okay, so and of course there are some papers have modification of this AMA algorithm. Okay. So this is the difference between ADMM and this AMA algorithm, because in one step you will also minimize the Lagrangian function. Okay, so it's going to solve the same problem as in the ADMM. Okay, however, we require that this function over here be strongly convex. Okay, in ADMM it was just smooth and convex. Right, this one must be strongly convex function, and then the others are quite the same. Okay, you have also the augmented Lagrangian, and the difference over here is that you have the Lagrangian, okay, Lagrangian function over here. Okay, so then you can minimize that alternately also, as like in the EDMM with respect to U. However, with respect to U, you just minimize the Lagrangian function. With respect to okay, which you have the non-smooth, non-differentiable part, you minimize that with respect to the augmented Lagrangian function, and then you update the Lagrangian multipliers. Okay, so this is the general complete AMA algorithm. Okay, so we will try to show some examples of this AMA for time series smoothing. Okay, okay, so time series smoothing. So this is the model that we wish to minimize using AMA for the time series smoothing. So we have this function 21 over here, subject to this this constraint. Okay, so this nabla j plus 1 is the jth order difference operator. So here we will, for this talk, I'll just take j is equals to 1. So you have the second order difference operator, which is, if you put that into the matrix form, is going to be something like this. Okay. Okay, actually it's almost actually it's a variant of the total variation denoising also. Okay, but using the second order difference operator. Okay. So this is the AMA algorithm for minimizing this problem. Okay, this the time series smoothing problem. So if you can see over here, this one you don't have to solve a linear system over here. Okay, this one, and then the rest is very similar to EDMM. Okay, so the advantage is over here. This one has this is a closed form solution. Okay. Okay, so this is some example data. I just smooth out some COVID data. So I got, we can take the data from this GitHub, Minister of Health GitHub page. Okay. So you can play around with the parameter actually. The parameter for this one. This one will, the lambda value will give you different smoothing. Yes, different smoothing. So this is the original data, and this is some smoothing. I forgot the value of the, I forgot to put the value of the lambda. What was the value of lambda over here? Okay, but don't worry, I will release the codes. You will see that I'll give you the codes for playing around with the experiments that we have in the slides. Okay, and yeah, so this one is just overlaying. So these are number of deaths and per day. Okay, from this is the date. Okay. So I think I'm not really into. I think this one is in, for those who are in time series play a major role in economics and some I don't know what else, but they usually look for trends, right? So they just want to get rid of these ripples. So this is one of the applications that we can do the time series smoothing. Okay, so the last algorithm that I want to overview, so is what we call the quadratic penalty alternating minimization algorithm, QPAM. Okay, so in this this QPAM method, okay, I will give an example on removing mixed noise. So the image will be a mix. The corruption of in the image will be a mix between a Poisson noise and a Gaussian noise. Okay. So this quadratic, this I'll just call this QPAM. Okay, the QPAM algorithm. It's a very simple algorithm which solves this type of problem. Okay, minimize. Also, still two functions over here. Okay. So originally it solved this type of problem. Okay, and the conditions for the F and G are similar to the ADMM. Okay, so what you do is first you add a quadratic penalty term with an auxiliary variable for this for U. Okay, so this actually acts as a constraint actually. Okay, so and then you will have this equation 23 over here. Okay, so you have this. This is the quadratic penalty that we add to this problem 22 over here. Okay, so this actually it's a very old method. Comes from Richard Courant. Can be traced back to Richard Courant in 1943. Okay, and it has been successfully applied to image processing for total variation image denoising in this paper over here by Wang, Yin, and Zhang. Also very highly cited paper in SIM Journal on Imaging Science. Okay. Okay. So this is the QPAM algorithm. So one of the different thing in the QPAM algorithm between the ADMM and the AMA algorithm is that we are just minimizing the primal problem. Okay, there's no Lagrange update. Okay, there's no Lagrange update. Just if you have, we just have here alternating minimization between variable U and V. Okay. Okay, so let's look at an example of applying this. Actually, this QPAM for mixed noise this part of the talk, I'm still working on this with one of my students. Okay, so hopefully that the equations are correct, because I got the equations from her. I asked her to prepare the equations, so hopefully the questions that I present after this is correct. Okay, still working in progress. So we are doing something related to mixed noise removal. Okay, so for mixed noise, we assume that the corruption comes from, this one is from the original degradation model. Okay, you have the blur, and then you have this U is what we want to estimate, and the additive noise. Okay, and then this observation Z is further corrupted by the Poisson noise, like this. Okay, so this P over here is the operation that adds the Poisson noise. So F is going to be corrupted by both Poisson and Gaussian noise. And this type of corruption is abundant in fluorescein microscopy and astronomical imaging. Okay, so we have this something like this, fluorescein microscopy and astronomical imaging. Okay, because Poisson noise is related to the photon counts of these the cameras that are used. Okay. Okay, so this one is the model. Okay, it's still a total variation regularization model. However, we are taking into account two terms for the data fidelity. As I mentioned in the early of the talk, that the data fidelity is related to the noise statistic, right? So this one is for the Gaussian noise, okay, L to norm. This one, if you remember the distribution of the Poisson that I discussed in the beginning. So if you do the map estimator, then you will get something like this. Okay. So this one is what we call the in the literature, in the image processing literature, we call this Kullback-Leibler divergence. Okay, so we're going to minimize this using the QPAM algorithm. And this, of course, this one is still the TV regularizer, and these are the parameters that will control the amount of noise filtering. So the lambda 1 is going to control the filtering of the Gaussian noise, and the lambda 2 is going to control the filtering of the Poisson noise. Okay. Okay, so so if you convert this one into the QPAM form, okay, so you'll have something like this. Okay, you minimize this function. Okay, you have all of this, and then we have this auxiliary variables for V, for du and ku. So it's going to be, we're going to minimize this. So you can see this. We have two quadratic penalty terms. Okay, for the two variables that we add over here. Okay. And this one is the overall algorithm for the QPAM to do the mixed Poisson Gaussian noise. Okay. Okay, so then you minimize this sub problems U, V, right? Oh, sorry, this one should be R. Okay, this one should be R. Okay, so U is still, you have the linear system, so it's not like the not like the AMA algorithm where you can bypass the linear system, but in the QPAM you still have to solve this linear system. So this is if you do the you differentiate this term and equate to 0, okay, and then you arrange to find U, then you will get this linear system. So this one is, you can see as this matrix over here as the A, and then this one is X is equals to B, right? A linear system AX equals to B, right? And then you have this the V subproblem, which is the L1 regularized problem. This one has the closed form solution similar to the ADMM and also the AMA algorithm just now. And this one is the R problem. This is a typo. The R subproblem, okay, has a closed form solution. If you do the simplifications of this, okay, you'll find out that this one is what you get for the closed form solution for the RSAT problem. Okay, so and then we will iterate this. Okay, so this is some example for mixed Poisson-Gaussian noise. Okay, so you have this, but in this case, the corruption is not just by the mixed Poisson-Gaussian noise; it's also with the blur. Okay, so we have here the blurring is from the Gaussian kernel with size 7 by 7 and standard deviation of 5. Okay, so we have, so this is the ground truth, this is the corrupted image. Okay, and then this is restoring using the QPAM algorithm. So of course you cannot get 100% similar to the original image. We still have some artifacts, but at least you can see that the noise are filtered out, and the sharpness is somehow you can retain the sharpness, right? But we still have the artifacts over here, like this smearing artifacts over here, which in the total variation literature we call this staircasing artifacts. So it's a very very popular problem in total variation image restoration. People have been trying to devising new types of total variation regression methods to get rid of this staircasing artifacts. This is one of the main themes in TV image restoration. Okay, so this is some setup for this problem. Okay. Okay, so this is the last slide that I have. So what we reviewed is actually some introductory or very simple introduction to image processing and restoration, motivation of optimization-based image restoration by Tikhonov-Vegrais image denoising, and then just a whirlwind tour of first-order methods. And then we discussed a little bit about ADMM or TV image denoising. And then we have the AMA algorithm, and we gave the example for time series smoothing. And then one of the advantages is that you can bypass the linear system. Okay, and then finally, as an example for the mixed Poisson-Gaussian noise, we reviewed the QPAM algorithm over here. Okay. So I think that is also, if you want to repeat the experiments, all the codes are in the release the codes in my GitHub page, except the mixed noise, because in mixed noise we are still doing some work on it, so I didn't release it yet. But the others you can find the codes in MATLAB codes. You can play around. Okay, so that's all from me. Thank you very much.
Yeah, thank you, Dr. Tamizi, for the insightful presentation. Now it's the time for the Q&A session. So, dear audience, if you have any questions, please type in the chat or you can turn on your mic. Yeah.
Yeah, Dr.
Yeah,
Chen.
any question?
Yeah. Dr. Chen, can you hear me?
Any questions from the floor?
Yeah, Dr. Chen, can you hear me?
Yes.
Yes, I can.
Yeah.
Yes.
Yeah, Dr. Tamizi, can you hear me?
Yes. Yes. Yes.
Yeah. Yeah. Thank you very much. And
You're welcome.
thank you very much for your fascinating presentation just now. Okay. Actually, I just have one question on the optimization part, right? So you mentioned that you're using the gradient descent, accelerated gradient descent, as well as a heavy ball algorithm
Yes.
for
Yeah.
your smooth part of the objective function, right?
Yeah. This one. Yeah. This model.
Yes.
Yeah.
So I'm just wondering, how are you going to handle your step size?
The
You
step
have
size.
you have
Yeah.
the step size,
The
right?
step size. The step size. We cuba in this experiment. Yes.
So try and error. So I mean,
Yes. Tyler.
is there any range? Is there any range or any guideline that you try?
Um, right now, no, but theoretically, it's 1 over the Lipschitz constant, if I'm not mistaken. So if you can find the Lipschitz constant of this, then you can maybe get an exact value. That is what I understand. But for this experiment, we try and error, try and error.
Okay. So may I know what is the values of the step size that you have been trying?
Uh, Over here, I think I have to open back my.
Oh, it's okay. It's
I
okay.
forgot to put it over here, yeah, because I just put the regression parameter which controls the filtering amount of noise filtering. The step size sorry, I didn't put over here. I need to check back.
Oh, okay, okay. That is okay. That is okay. So
Yeah.
actually, I might, I mean, I'm suggesting maybe you can use the Amijo, line search also, the inexact,
Oh yeah,
step
line search is
size line
method. Yeah,
search.
yeah.
Yeah, I think,
We didn't use that. We didn't use. Yeah.
yeah, yeah. At least the Amijo line search or the UF search line search condition, it can guarantee the descent
Mm,
properties of the algorithm. Yeah,
yes.
if it is trial and error, I think it's quite difficult to prove the convergence of the
Yeah.
algorithm, right? Yeah.
Yes. Yeah.
Okay. Then another question, sorry, yeah, Dr. Tamizi. So
No problem. No problem.
yeah, you have only tried for gradient descent, heavy ball and accelerated. Did you I mean, did you ever think of trying other optimization algorithm, for example, quasi-Newton or maybe spectral gradient?
No, I haven't tried, but I think it's going to be the results in terms of the noise filtering. I think it's going to be the same, but probably in terms of convergence, probably the speed is going to be different because this one, because for because when we minimize this Tikhon of function over here, uh, it doesn't whatever algorithm that you use, this model will, in terms of the output of the noise filter, output of the image, is going to be blurred, because this one is for those who are familiar with signal processing. It's actually this model is actually the Wiener filtering. So Wiener
Mm.
filtering, if you those who know about Wiener filtering for images, it's going to be blurred. What I think, even if you use some other methods, like you said just now, uh, the results in terms of PSNR, the quality is going to be the same. Probably just the convergence time and the number of iterations is going to be probably going to be improved lah. That's what I can comment about.
Oh, okay. Okay. Sorry, for last questions. So I'm just curious, for your current slide, right, that you are showing, you
Yes.
are using lambda equals to 0.85 for gradient descent, accelerated gradient descent, and lambda equals to 0.055 for heavy ball. So is there any rationale to choose these two values, different value for different method?
This one is trial and error also. The one that we get
Okay.
here is the best that we can get. So these are the values. That's just trial and error.
Okay, okay.
Mm.
So the lambda actually is a penalty parameter, right?
Yes, the penalty parameter. So depends if it's for example like too low, then you get very low noise filtering. High, you get good filtering. Just trial and error over here.
Oh, okay. Because I see your lambda, your penalty parameter here, um, is quite small because when I try for my own for my research, for my own research, my
Mm.
lambda that I try is like more than 2. I mean, sometimes I put 5, sometimes I put 4.
Oh,
Yeah, so that's why I'm
I
a bit
I
curious. Yo.
Yeah, because I also have similar experience. But what um, from my experience lah, what I know is because sometimes the way you formulate,
Yes.
because sometimes some of my algorithm also comes large values also. Uh, because
Yeah,
sometimes
yeah.
I formulate instead of like 1/2, some of the algorithm I formulate I put the lambda in front, lambda over 2, and then this one does not have the parameter. So what I notice is it will become some change over there because of the how you formulate. At least
Yeah.
that's from my experience lah.
Yeah. Okay. Yeah. Okay. Thank you very much,
Okay,
Dr.
welcome.
Tamizi. Thank you. Dr. Chen, I have no more questions. Thank you very much.
Okay, thank you, Dr. Tamizi and Dr. Singh. Yeah, any other question from the floor? So yeah, if no, then once again, a big thank you to Dr. Tamizi for sharing his expertise with us today. We hope you found this talk enlightening and valuable. Stay tuned for more events like this in future. Take care and goodbye. Thank you.
Bye. Thank you all.
Thank you very much. Thank you.